Today we're going to take a look at Wireshark. I don't have a presentation for that, but I would like to give you a kind of quick overview of Wireshark, and also we will do some little bit basic analysis, and then we will take a look at the advanced analysis, like decrypting traffic, wireless network traffic analysis, or maybe a telephony analysis and things like that. So those kind of traffic you may see during your live, even if you're in a network guy, or maybe a forensic investigator, or maybe even an incident response handler. So you will probably see something like that. So first of all, Wireshark, why we like Wireshark and why it is so good. So I always give this example. So if you go to wireshark.com/download/automated, and you will see that there is a source line of code section. And this is actually a really important section because it shows you how many lines is Wireshark contains. So if I scroll down, this actually gives you a better idea. So it is developed primarily in ANSYS. That's why it is fast. And little bit code from C++. And also, as you can see, there are multiple other languages, even Python, Pascal, even assembly languages are also included. But I want to give you a really important message here. This Wireshark stuff is actually really important because it includes almost 2.6 million lines of code in total. So it makes actually one of the biggest open source project on this planet. And actually, it's maybe the second biggest project, coming after from Linux. So this is really huge. And if you hire somebody with some, hourly rating, it will probably cost you approximately $100 million to develop such an application. So that's really extensive amount of work, and it is free. Not only free, but also it is ad free. So that's actually a really good thing to have, because there are a lot of free tools, but it's overwhelming you with a lot of advertisement. So that's why I really respect what these guys are doing. So we're going to use Wireshark to analyze a bunch of traffic, and I would like to start with some of the easy peasy examples. So first of all, I will use T50. So when we start to analyze a package, so a lot of people are doing a mistake that they are just scrolling down all the way up, all the way down, and trying to figure out what kind of a package is included in that. So it is useful in some cases. So for example, if you already addressed that this is the kind of a traffic that you already filter that out, and you know what's going to be included in this traffic, that's a good idea to scroll down all the way up, all the way down. But if you're dealing with a package traffic that you have no idea what it looks like, so the best shot is actually to use some Wireshark tools to come up with an idea that what does this look like. So for example, this one is actually a typical example that if you scroll all the way down, all the way up, it won't give you a kind of a sense, right? Right? Anybody have any idea what does this look like? Or can tell me any idea? So, huh? Yeah, routing protocols. There are a lot of routing protocols, but also ESP is not a routing protocol. RSVP is not a routing protocol. ICMP is not. So there are routing protocols, but there are also other layer 3 protocols. So that's an interesting traffic. When you look at it, it doesn't make any sense. But there are some fields that make sense when you look at the packages. So first of all, you need to take a look at the number of packages. How many packages are included in this capture? If you look at the right bottom corner, it tells you that how many packages included in this package capture. So we're talking about 163,000 packages in this capture. So it's a lot of packages, by the way. We cannot analyze by eye. So what we can do is, first of all, we need to use the statistics, okay? By the way, before going to the statistics, so why I just decided to open this with Wireshark, why not I use Tshark? It actually depends on the, oh, thank you, Richard. It actually depends on the size of the package, right? So if you're dealing with a package less than 500 megabytes, then you can open it with Wireshark, so it's not going to be a problem. So these guys are really small ones because I already filtered that out in order to give you a clear picture. But if you are dealing with a package that's bigger than 500 megabytes or maybe close to 1 gigabyte, that's not a good idea to open with Wireshark. Even if you open that, you will probably have a lot of difficult time to analyze the package, because every time you write a filter, Wireshark needs to go over the 1 gigabytes of data. It's a lot of work. By the way, remember, 1 gigabyte of data on disk doesn't equal to 1 gigabyte of memory in your memory, right? This needs to be parsed, so that's why the parsed data will take more space. So for example, if you are opening a 1 gigabyte of pcap package, it will probably allocate at least 4 gigabytes in your memory. Yeah, so that's the idea. So this was a 14 megabytes, so that's okay to open with Wireshark. And then we will take a look at first of all, I always look at the protocol hierarchy, because it kind of gives me an idea that what kind of a protocol is included in this traffic. So if it's an unusual traffic, if it's it doesn't look like a normal regular traffic, then I usually suspect a kind of a float or maybe other traffics. So first of all, what a normal traffic look like in a normal enterprise. So give us an idea, what kind of a traffic do you usually see in normal network environments? Yeah. Web traffic, good. Yeah, HTTP, HTTPS, those are the good traffics that you see. Approximately 90% of traffic as HTTP, HTTPS, and a little bit SMB traffic, and then a little bit other traffic like BootP, DNS, SIP maybe, or maybe remote desktop protocols and things like that. But let's look at this one. So this is saying that, hey, there is an IP version 6 traffic, but it's a one package only, and almost 100% of them are IP version 4, which is nice. I mean, that's okay. We usually see a lot of IP version 4 traffic, and it's saying that 20% of them are UDP traffic. That's interesting. I usually don't see 20% UDP traffic in a normal environment. And if I collapse this one, it's actually telling you that 10% is TCP, which is really unusual. So if you're looking at traffic with 10% of the TCP and 10% of other traffic, so 90% of other traffic, that's extremely unusual. So,
are you saying it should be more?
Yes, that should be more. TCP usually, approximately 80% of traffic usually is TCP. So that's why this is unusual. And interestingly, RSVP, Open Shortest Path, IGMP, ICMP. So these guys also have approximately 10% traffic each one. So that doesn't make sense. How a network can generate this many distributed traffic in a time frame? So it is unlikely, but we can assume that somebody has just filtered this package according to some of the traffic, right? So that might be an idea that, okay, that is unusual, but that's because of the export filter. In this case, what we usually do is we look at the I/O graphic. Okay, why I should look at I/O graphic? So there is actually a good reason for that. If you look at the time of the packages, you will see something interesting. So they are coming from external IP addresses, and you will see that there are local IP addresses and actually one IP address. And if you look at the package, so in 8 seconds, you see that even 8.0.788, you will see a lot of packages, right? So in a millisecond, I'm getting a lot of packages. That makes this traffic a little bit unusual. That's why I tend to take a look at the I/O graphic. Is this a bursted traffic? Is it a fluid? Something like that. The easiest way to understand the fluid traffic is I/O graphic. So when you open the I/O graphic, Wireshark may give you an filter here. You need to take a look at that. Even if there is nothing here, you may see something like this. Empty, you don't see anything. Don't worry about it. So we need to add some traffic here, and we need to take a look at that without any filter first, okay? No display filter. And you can come up with either line or bar graphic. I prefer bar graphic usually. So this is a traffic, how it's flowing. So we're looking at 1 second frame, right? So in the first second, we see that there are 18,000 traffic. In the second second is actually a little bit less, 2,000. But the rest of the 7 seconds actually is coming from approximately 12,000 IP packages. And remember, these 12,000 IP packages in 7 seconds are coming from 5 or 6 different IP protocols, which means somebody is doing an IP protocol float to your environment. Why do you think they do something like this? So what makes this traffic so good to use them as a float? So yeah, obviously it's the float traffic. As you can see in a second, it's sending a lot of package. Why this traffic? Why not it is SymFloat? Why not it is other protocols? Why IP protocols? Actually, this is coming from a real case. This is actually attack to my network. When I see that, I like the idea, and again, so because first of all, in IP protocols, you can spoof the source IP address. That's why they usually prefer to use the spoof IP address. Second, usually network administrator configure their protection devices to block SymFloat or UDP float, any kind of a layer 4 protocol. But these guys were smart enough that, hey, if I use a layer 3 protocol, probably it is allowed. Because nobody expects an IP protocol flow to your environment, right? And a lot of network engineers actually don't know these protocols. Even they don't know if they exist. That's why these guys are taking advantage of spoofing IP address, source IP address. Second, they know that your protection device is not well configured for different IP protocols. So this is one example. And now we will look at to one of the famous attack vector. This one again, when we open this, pcap file, we can scroll down and take a look at what it looks like. This one is obvious. In this case, it will work. You see that there are a lot of, layer 2 traffic here, and obviously it's an ARP traffic. So that's actually making sense, but I still prefer to take a look at the protocol hierarchy and see what's going on. Definitely almost all of them are ARP traffic, makes it outstanding traffic. We need to take a look at what's going on with ARP traffic. Let's filter that out. I can use the Wireshark display filter to have a look at what's that. So first of all, this is a network. So I can actually just disable any column if you don't want to see. So and the destination port. So so these are the packages that are coming from some device with ARP. And if you look at that, so times are close, but it doesn't look like an float traffic. I can easily take a look at the IO graphic. But in this case, instead of getting all packages, I want to take a look at the ARP protocol only, right? So display filter is going that section. So whatever you display filter you're using, you can use for drawing a graphic here. So when I did that, I need to check this box. Obviously, there are a lot of ARP packages are coming. Is this a float traffic? Not exactly, because number of packages, if you look at that, every second, almost there are 9 or 6 or 7 packages, right? So that's not much. It's not a float traffic. Float traffic, usually, you see thousands of packages in a second. That's not float. So what is that? Obviously, an ARP package, if you know that ARP protocol, it stands for Address Resolution Protocol, and if you send a lot of ARP reply to somebody, it will cause a damage on the server side. So let's take a look at are these really ARP reply or ARP requests, right? So obviously, source MAC address are always the same, then destination MAC address are always the same. So that's why this seems an all reply package. And by the way, I can create a filter for that. Prepare filter or select it by clicking on any section in the details section. If you right click on that and if you click on prepare filter or select it, Wireshark will do the good job for you. But in this case, actually, I clicked on wrong place. Let me do it again. Let's get rid of this. And this one is actually reply. Option code is reply. So I will right click on that and then say or select it. So this gives me that ARP.opcode is equal to 2, which means reply. So if I filter that out, remember number of packages are displayed are now 970. So if I click on that and make it filter, again I am seeing that 970 packages. So we're looking at all reply packages from one server to another server. And I can take a look at the endpoints here. It will also give me that the packages are extremely outstanding for two source and destination, which makes that somebody is trying to inject something to somebody else. This one makes it attacker. This makes it as victim. But what exactly is that? So how do we read that? And Wireshark is actually giving us a good opportunity to see that. So this is attacker, and attacker's MAC address is VMware ending with E086 and B8. And if you look at that, the package is sent to this guy, and he's saying that 192.168, 132, 131 is at this MAC address. And do you figure that out? What is that MAC address? Itself, right? He's actually trying to poison the ARP cache or the victim by saying that I am the IP address. If you are going to go to this IP address, come to me. Which means it's a layer 2 attack. Somebody's trying to poison somebody else's address cache, which is actually will eventually end up in man-in-the-middle attack. This is how it look like in a package level analysis. So, so let's look at a little bit layer 7 attacks, and I would like to show you first of all an easy one first. Which was that? Okay, let's use this one. Again, we're looking at approximately 100 packages, which is nice. We can scroll down, try to figure out what's going on, but I usually prefer the same way. Have a look at the protocol hierarchy, what kind of a traffic I'm looking at. Okay, TCP and HTTP. And HTTP data is actually link-based text data, means that HTTP data itself. So probably there must be something wrong with the HTTP traffic here. Let's look at what's going on, how we can make it filter. So first of all, I can get rid of these blue packages by putting an HTTP filter here, right? That will help me to kind of look at what's going on, what does it look like. So obviously there are some URLs that seems interesting to me. I can take a look at these URLs with naked eye because it seems an easy one. So when I look at that, there is a URL here, and somebody is sending title is equal to DNENEE at action search, okay? And getting an answer 200. Another one is sending Iron Man and getting an answer okay. Another one, but this time there is an interesting item here. So which is the %27, right? What does that mean, %27? It's single code, right? It's a famous, if you are going to memorize something in URL encoder, you have to memorize single code. It's 27. Because this is really a red flag for a package. If you see that somebody is trying to send a single code, here might be somebody like a surname with a single code, like McDonald's or whatever that surname is. So some surnames includes actually a single code, or he must be attacker. So being an attacker is actually highly likely than having a surname with single code. That's why when I see that, I usually assume that they're attacker. And this guy is actually sending one single code here, another one here, right? So it's actually 3 times he's trying to get some data from the server, and the system is kind of replying in a way that it can give an idea. So if I right click on the package and if I say follow TCP stream, I will see that in a better picture. So this time he's sending just a dynamo and getting an answer here. And if I scroll all the way down, actually in order to make it clear to see, so I can do this. So let's see only the attacker's packages, right? Obviously dynamo, Iron Man, title with single quotes. Okay, so I want to take a look at the response of the last one. So this time I will scroll and actually let me see the entire conversation. Let me scroll all the way down and see what's going on. So the server is responding with HTTP 200. Good. So obviously there is nothing to worry about, but you have to take a look at the content of the document. So here is, you can see that error. You have an error in SQL syntax. Check the manual that corresponds whatever that MySQL. So this is actually a indication of that your server is vulnerable to SQL injection. Is it obvious that this guy has exploited the server and extracted data? No. Is your service vulnerable to SQL injection? Yes, that's right. So what we know is this is actually a proof of SQL injection. This is how we can, find a SQL injection. You can look for a single code, of course. By the way, if you would like to search only single code, you may take a look at this. Use this. So frame contains. This is actually my favorite filter. Frame contains can search for anything for you. So for example, if I say 27, it will give me all the requests with 27 as included in that. So Wireshark can help you on that a lot in order to find some malicious things. Of course, it doesn't have to be a single code, but you can search for select, union, and things like that. And you can put a lot of filters cascaded here by using OR filter like this, or maybe AND filter, depending on your needs. So that was also an easy one. So let's have a look at the little bit difficult one this time. So plain text traffics are easy to understand, and actually we're not going to drill down all the plain text traffics today because we already covered the plain text traffic in the previous session. So this time we would like to deal with a little bit encrypted traffics, like this one, like 802.11 traffic, which is a wireless traffic, and also encrypted traffic. We will take a look at that and try to understand how we can kind of parse them and see that. So this one is actually a really bit interesting traffic. If you look at the protocol hierarchy, you will see that it is TCP and TCP data. What does that mean? There is no HTTP here. What does TCP and data mean? It doesn't mean a lot. And if you scroll down, you will see that it's not a fluid. I can take a look at the IO graphic. It's also okay. Obviously, this is a TCP graphic, TCP connection, but there has to be some clue to figure that out. What does it look like? So in this case, you need to take a look at the port, okay? Because Wireshark can do its best to give you an idea that what protocol is running. So if he can see that there is an HTTP traffic, the protocol column right here is going to be HTTP. If there is an encrypted traffic that Wireshark can't decrypt the traffic, it's going to say you the highest protocol that he can recognize. It can recognize. In this case, it is TCP. So it is TCP, but we need more information for that. So how can I figure out what kind of a TCP traffic I'm looking at in a package capture? So I look at the source and destination port and try to find out if there is a familiar port, right? So obviously this one is destination port is 844.8443, which means probably this is an HTTPS traffic. Okay. So in HTTPS traffic, we need to know what's an HTTPS traffic look like. First of all, HTTPS works like starts with SYN, SYNAC, ACK, the three-way handshake, and then client send hello to server, and server sends a hey, hello, and then exchange the cipher suites, and then decide to a cipher suite, and then download the server certificate, and then start the communication, right? So this is how an HTTPS traffic look like. But let's take a look at this one. SYN, SYNAC, and push. That's interesting. Let's try another one. Any SYN, SYNAC traffic right here. SYN, SYNAC, and then push. That doesn't make sense. I need to see something SYN, SYNAC, ACK, and then client hello, server hello thing, right? This does not exist here. So that's why this is not a normal HTTPS traffic. So what it can be? So we need to take a look at the outstanding things, okay? So if you look at the package capture here, the biggest outstanding thing is obviously this push statement, right? It's sending some data with a push with 223 bytes, and then server says ACK, and then server sends an push message to the client, which is 1,000 bytes. That's interesting. That makes really interesting. And in this case, I usually try my best to see what the package content look like, right? So here, for example, is a 1,000. Probably it is encrypted, but this time it seems that there are some plain text thing. So I will probably prefer to follow the TCP package. Oh, what's going on? Follow TCP stream here. Then it will give me some kind of a traffic. So this is interesting because this is an HTTPS traffic, right? SYN, SYNAC, ACK, and it's running on HTTPS port. But the protocol definition seems an interesting SYN, SYNAC, ACK, and then push is coming. And second, there is no encrypted traffic. I see a plain text traffic here, right? So there's an email address here. So that makes this interesting. And let's take a look at the other stream, right? The first one is actually at least seems an interesting. This one is empty. There's nothing. The third one is empty. Fourth, fifth. Okay, this one is actually the seventh one. And again, I am seeing exactly the similar thing. So this is actually a kind of a plain text traffic. And appended that, there are some contents with some information and with some empty payloads here, right? So instead of looking at ASCII, I can change it to a row view. So it will also give me an idea that, so see that there are a lot of zeros here. Okay, so anybody have any idea what is this exactly? What is zero is coming from? Yes?
I think it's heartbeat.
What's that?
Oh,
yeah.
Oh, this is an example of a heartbeat.
That's right. Two right answers. Yeah, this is an example of heartbeat. And actually, obviously, these zeros coming from the empty space of the memory. It is because you know heartbeat is how it works. So heartbeat is something like this. I am telling you that hey, let's exchange some package to keep the connection alive, right? I'm saying that hey, with a 64-bit data size, and you're supposed to give me a 64-bit data, but I'm saying that hey, and it was a 1 kilobyte data. I'm spoofing here and saying that, hey, it was a 1 kilobyte. Give me a 1 kilobyte of data because I also tell you, normally OpenSSL library, when you say, hey, and allocate on 64 kilobyte of data, it is allocating 64 kilobyte of data in its memory and then replying back to you exactly the same data section that you are asking. So that's how it keeps the memory connection alive. But in this case, I'm saying it's 64-bit, but asking you one kilobyte of memory. So what is OpenSSL library is doing? Okay, 64, and then entire 1 kilobyte of. Here is your reply. That is coming from the memory of this particular operating system. That's why it includes a lot of connection to it, belongs to other people. So obviously, somebody is having a connection with this server with some HTTP content in the memory, and I see their form fields, even their password. It's supposed to be somewhere here. And also connections. Probably this is a private key that's being constructed for the SSL connection. So this is kind of an interesting traffic that you can see in vulnerable environment.
And you can do the session hijacking also because
exactly. You see the cookie? Yeah, you can just reply. Use the cookie to attack. So that is Heartbleed. And do you want to try any of this? I also obfuscated the name, so can I give you an idea that what is that? So would you like to see any more, or would you like to go to the other section because we need to try more? Okay, I will keep that as a no, and then I will go to this one. So I prepared a couple of small examples for you. Has anybody used Wireshark for VoIP traffic before? Voice over IP. Wireshark is really capable of doing a lot of great things with voice over IP. That's why I actually would like to include some of the examples for voice over IP too. So in this case, this is a traffic that you can capture during the network, and Wireshark has really good capabilities to play around with the VoIP traffic. Again, I will look at to the protocol hierarchy to understand what's going on. Obviously, there are a lot of real-time protocols. So real-time protocols means that there is either face-to-face or let's say video conference or maybe VoIP conference. So that is VoIP traffic, and if I scroll down, I can see that they are right here. This time we're lucky that Wireshark already addressed that this is a traffic with ITU-T kind of a protocol, and it has been encoded with G711 codec, and the sequence number are being parsed by Wireshark. So it may not have to be always the case, but this one is okay. And if you're lucky and you see that the VoIP traffic is properly decoded by Wireshark, you can use the telephony section and then look at to the VoIP calls. So here we have a VoIP call, and as you can see, there's a play stream here. If you click on that, and let me choose both of them. Okay, let me play this. And try this. Can you hear that?
Testing 1, 2, 3.
Fair enough. So, and it doesn't have to be, a plain HTTP traffic to decrypt it, or let's say reconstruct the traffic. VoIP traffic without HTTPS equal to wiretapping, and also anybody can listen as SIP traffic. It's not too complicated, so please pay attention to using secure SIP. Use an encryption on your SIP conversation, okay? Because it's really easy to decompile and also decode the traffic. So I have another one. This is a little bit challenging, but this is usually the case because Wireshark is not perfect to understanding the traffic. So here again, it's a RTP traffic, but this time, as you can see, it is saying UDP here. Some of them are actually being parsed. But let me actually give it a try. Maybe I just let me see. Maybe it is because of my decoding. Is that the case? Let me see. Port number, UDP, destination port. Okay, it's not. All right, no, it's not. Let me see if it is actually being parsed, or if it's not, I will probably do that. So in this case, I will look at the RTP streams. Why? Because I can take a look at the VoIP calls. You will see that there is nothing. So VoIP calls are different from RTP. Oh, it is. I didn't know that. It's supposed to be RTP only. Obviously, this one is a SIP traffic too. So there are two different protocols actually. SIP is one protocol. Real-time protocol is actually an encapsulator for that. Sometimes it's not parsing. That's why I usually prefer to use in the telephone section an RTP and take a look at the RTP streams, if any. So in this case, there are some traffic and it's been found, and then you can say that, hey, find me the reverse direction of this conversation. It's just highlighting that, and you can say that analyze these two conversation, and you can see that it actually starts, ends, and kind of a bandwidth, and also status of these each packages, and how long will it take to listen that, and then I can start again the same thing.
Por el Atlas, obviamente.
This is not me.
Bueno, sí te escucho bien. Ah, ya ves, eso sí se escuchó, ¿verdad? 05 1454 0005.
Okay, so this is the traffic. First of all, as you can see, guys, it is taking a lot of time to compute, and let me actually quit that because it's going to be mislead you. So 65 megabytes of traffic here. It's okay to open with Wireshark, and when you open that, you will see that there are 400,000 packages. We can do our best to take a look at the protocol hierarchy, and in this case, we will see something really interesting because you will see that it's not a familiar protocols. Wow, that's really good, huh? So obviously this is a layer 2. Data frames are encapsulated with IEEE 811 wireless LAN, which means this is a wireless package, wireless packages. That means you cannot see the content of the wireless packages unless you don't know the encryption key. So obviously, if you know the key, I will show that you can put the key and decrypt the traffic, but I would like to put a little bit fun here. That's why the key is not available. So what can you do to find a key of a traffic? Okay, so first of all, we need to identify that what kind of a traffic we're looking at in this traffic. So there is a wireless section here and VLAN traffic here. If you look at that, so the SSID is right here, VOOT is the SSID here, and the protection is WEP. Good. But no, don't smile. In order to make that happen, I put a lot of effort today. VEP traffic is really hard to find. But there is a way to crack VEP traffic. Obviously, cracking a pcap package with a brute force AirCrackNG is easier, but I would like to use that. Even if you don't have anything, you still can use AirCrackNG to crack password of a connection. So what I'm going to do is I'm going to boot up my Kali Linux, And in Kali Linux, actually, there are a lot of good tools to decrypt the let's say crack the password of a package. This one is obviously the easy one because I already deliberately injected some IV vectors and generated enough IV vectors to be cracked easily. But this was a case many years during early 20s, let's say. So what we do is copy this traffic first. Where is that? I will copy this traffic and put it in my Kali box, but there's something missing here. Okay, yeah. Let me get rid of this. It's actually the same thing, but let me replace though in order to make sure that I'm not cheating. So, in order to crack a wireless password, actually there is a famous tool which is called AirCrack, and next generation is available for that. So this is actually running for in a lot of platforms, including Linux, Windows, and Mac OS. So it's easy to use. Actually, it's not that too difficult. So there is actually a way good documentation. If you don't know anything, just put AirCrack NG and hit enter. It will display you the help. But pretty straightforward. All you need to do is AirCrack NG and then give the package. So AirCrack. By the way, AirCrack has a lot of suite, and it's not only limited with AirCrack. If you would like to play around with wireless traffic, it can do a lot actually. For example, AirDecap can decrypt the traffic for you if you know the encryption key. AirCrack is responsible for cracking things, of course. Airbase is actually setting up a base station on your computer so you can create an evil twin. And Air Replay is actually kind of a wireless replay traffic to DDoS and network. And our AirODump is responsible for dumping the wireless traffic to your disk. So remember, if you start Wireshark to filter your traffic or maybe capture your traffic, you will not see something like a 802.11 traffic, right? So let me actually show that. So it's actually now sniffing my traffic, as you can see. But obviously, this is not a wireless traffic, right? It's obviously the traffic. Of course, it's not a plain traffic. You don't expect me to connect a shared wireless network without VPN, right? So that's why it's a VPN traffic, guys. So, yeah. So I'm connected to Nova Labs, but I don't see any wireless traffic here. But if you use something like this, yeah. Has anybody used something like this before? TP-Link? Okay. This is actually fairly common if you are doing a wireless penetration testing for organization. What it's doing is it is capable of not only sniffing your traffic, but also can sniff the air. Okay, so it's a totally different thing because your wireless cards are built in. It is hardware, doesn't sniff anything other than its traffic. Okay, because air is shared space. If your wireless card sniff everything, anybody can start doing an air crack and try to crack the wireless password. So that's why hardware providers always embed a chip that protects you to sniff anything on the air. But these guys are capable of sniffing anything on the air. But you need to choose the channel, of course. You cannot just sniff every single channel because it has to be aligned some channels, or it can sniff that channel. But this can sniff anything like you see in the VEP traffic. So this is how you can get the capture of this 802.11 traffic. Okay, yeah. So when you have something like that, you can also set up an able twin and let your people to connect, or even not, you still can sniff the air. And if you know the wireless passwords, yes, you can crack it. You can decrypt the traffic, and then you can see the traffic. So there's actually a big misleading. If you are using a wireless network with password, it's like here, it doesn't mean that we are secure from each other. So that means that we are in the same layer 2 network. I can sniff your traffic. You can sniff my traffic. you know, that's actually a kind of a man-in-the-middle attack, but it's happening on the air. So in this room, actually, anybody connected to wireless network are actually doing a man-in-the-middle to each other seamlessly. So if you guys have something like this, you can send back traffic, send this traffic, and then by using the password, you can decrypt the traffic. That's that easy. Okay, so that's the aero dump stands for. When you set this thing, use aero dump to dump the traffic. But let's go back to air crack. So air crack is responsible from cracking things, and it's pretty straightforward to use. All you need to do is just give it a file name, and if you have the ID vectors already, you can use that to crack either. So I will use the capture file, pcap file. Actually, it's since it's a version 1 pcap, it's actually a cap file. But aircrack cannot crack pcap ng files. Okay, you need to save a pcap extension. In that case, you can use aircrack, and then it can automatically find that it is a VP traffic and then try to crack that. So that's in this case, it's pretty straightforward. So let's do that. And it was evidence05.pcap. If I hit enter, it's enough because there was enough number of initialization vectors, and the key is 4A70 B508CD. It doesn't look like your wireless password, and of course, the wireless password was not the answer. So while encrypting your traffic, the wireless password is not being used for to encrypt your traffic. It actually is using a binary representation of this key, and then it's being used for encrypting the traffic. So where the password is coming into play, and if I know the password, how can I decrypt the traffic? It's why if it's not being used to encrypt the traffic. This password is used to transfer that key. So if you see that at the beginning of the communication, if you see that your client is generated a key, something like that, and it's been encrypted with robots for you, there you go. Which means if you begin to sniff my network right now, it's too late, guys. I came here at 5:15. I just connected, so you lost that. If you lost my negotiation package, you cannot decrypt my traffic. Okay, so we have the key. So what are we gonna do? What we do is we will copy this traffic, and then key, and then use it in Wireshark to decrypt my traffic. So let's open the evidence 5 again. Okay, let's give it some time. Yeah, there we go. And then use preferences on Wireshark. There are protocols here, and you can use other protocols to optimize. But in this case, since it's an IEEE 802.11 traffic, there is a decryption key section here. So it's pretty straightforward. If you need to add something, you need to choose the key type. Is it VPA personal or pre-shared key, or VPA password, or it doesn't support VPA enterprise, by the way. And the key is this one, okay? And that's all. If you just save this and say okay, it will rescan the packages again, as you can see on the left bottom corner. And interestingly, this time we will see something interesting on the statistics section on the right down corner. It's supposed to be right here. Anyways, so let's take a look at the statistics and protocol hierarchy again. There we go. So this time, again, it is 811 traffic, but I see that there is a link local, IP version 4, and then UDP, TCP, and TCP, SMTP, and HTTP. In HTTP, we see that there are a bunch of media types also being transferred, but also there is an Internet Message Access Protocol also exists. So that's cool, right? So we see that, and let's play around with that. I mean, I would like to see something with TCP, okay? And I can start, just type the filter, and then it will bring me to all the TCP traffic here, which is cool. So again, I can do anything that I did before. So for example, there was a question for this one. What was that? Let me look at it. So we actually start from the beginning. Yeah, what is the AIM body name? So that's obviously instant messaging protocols. We can take a look at that, but I would like to use Tshark at this point because, as you can see, there are a lot of packages, and I don't know what's going on here, and you know, that might be an encrypted traffic, and I can write a filter, but it's taking a little bit of time. For example, HTTP. Yeah, I mean, it's still manageable, let's say. Not this one, but the other one, we will definitely use Tshark. So yeah, here we go. We have a bunch of HTTP traffics here, and I need the URLs here. But so I can get the get sections here and see that if it's any contains any body name to figure it out. So what I'm gonna do is request method is get, and I will say that this is going to be my filter. So HTTP.request method is get, or maybe this is a post request, right? So let me copy this and type post. By the way, Wireshark is case sensitive. If you put like this, it's not going to work, okay? So you have to put exactly this what it's look like. So get is actually uppercase. You have to use uppercase in order to get that. So if I filter that out, I will see a bunch of get requests here, and I can take a look at them and figure that out which one is exactly my American Online thing. But there is a better way to find it out. So for example, and I can say that frame contains, let's say, send, okay? And maybe it's uppercase, lowercase, but I will try. And maybe I can search for AEM. So what is wrong with the filter? Why it is yellow?
Because it's frames.
No, it is frame, actually. It is correct. And actually, this is a signal that says neither wrong nor true.
Because, and you have not put ampersand.
No, it's not.
Oh.
Okay. It's actually an ambitious filter, and when you type a filter on Wireshark, and if you see the yellow, that means that this statement is always true, or always false. Okay. So, for example, I'm saying that it is get or post and send. So Wireshark needs to know that which one is going to be processed first. So you know that in computer science, there is a term used, what's that? Precision? Hierarchy, yeah, precision or hierarchy, what I don't know. But you have to tell exactly what is going to be the run first and then which one is going to be run first. If you need to run this as a block, then you have to put a brackets around that. So it will understand that, okay, run this as a standalone filter and have a look at if it contains anything like send, okay? And then in this case, I will have a better filter and also probably have some good indications. No luck. Okay, let's go to Tshark. So why I prefer to use Tshark? So first of all, I can actually so since we have TCP traffic here and it's been decrypted, I can actually filter it as TCP and then on file menu, and I can say export specified packages, okay? Or maybe let's do this TCP and then hit enter. Let's get TCP packages first because I need to give the decrypted traffic to Tshark because Tshark itself cannot decrypt the encrypted traffic. Okay, Tshark, unlike Wireshark, doesn't have a capability to decrypt. So that's why I have to give this packages as a standalone capture. So for example, this one is going to be my 5.pcap, just like this one, and it's going to be the encrypted one. So yes, please. By the way, while exporting that, have a look at the filters here. It says all packages and only displayed, okay? I'm not saying the captured packages, instead the display packages. So if you choose display packages, you will only export the displayed packages, and it's a good idea usually because all packages, if you export it the same way, you will end up with the same thing. So it's going to be huge, a lot of packages. And yeah, so let's at this point use Tshark and what it's doing, how we can use that. So first of all, why Tshark? Why we need that? So as you can see, guys, so on Wireshark, I have a lot of flexibility to filter that out, you know, get something. But you see that the URLs, all those things, I can't use the command line tools flexibility, right? Remember when we're doing the command line tools, we can play around, sort, unique, and then grab something, right? So we can play around, but unfortunately, Wireshark doesn't have that capability. You have to precisely find what you are looking for in order to tell that. But Tshark can integrate with you the command line tools, so you can use exactly the same command line tools with the output of Tshark. So it is pretty straightforward to use that. Actually, you need to specify the file, or it can capture from the interface too. But I usually prefer to use a file, and you can use that -r an inline file. So that's why I will use something like this, and 5.pcap is going to be my man. And if I hit enter, you will do big mistake. Okay. Remember on a command line tools, we never hit enter, right? We always put some termination at the end, so it will help me to figure it out what's going on, what's wrong here, what can I look at it. So as you can see, look at it. So it's a plain text, and I can use command line tools, right? So that's pretty good, and I can capture HTTP, and I can look for specific things, and then maybe get something. But I would like to first get some fields from this section. So what I'm gonna do is actually, let me show in the help section. So this is actually really good. First of all, it can take filters, display filters. So you can filter the pcap while you are reading. So that option, I'm gonna show that, but there is also another cool feature that you can choose some fields, okay? And then you can provide it as a column. What is that, -t? Yes, this one. So this is actually -t in combination with -e is the life-saving thing, because these are the columns, good columns, source IP, the time, the number of the package, and the port protocol, some of the description, but it's not exactly what I'm looking for, right? I need to get HTTP request method, right? That was the piece of the things that I was looking for, and unfortunately it is not here. Although it is here, it requires a lot of effort. That's why I will say that Tshark, can you, actually let me, a little bit, okay. Let's start with this one. Okay, so what I'm going to do is I will use -t and fields, which means, hey Tshark, while reading this package, I will give you the fields as a column, so please show only them to me, not all of them, right? And these columns are going to be -e and http.request.ure. How do I get this thing? Remember what you did in the Wireshark, right? So what we did is actually http.request.method and http.request.ure as actually exactly the same thing that you are doing in Wireshark. So it's they are using exactly the same filter syntax. So that's why I can use this, and I can take a look at that as again head. I'm about to die, you know that, right? So as you can see, guys, we have the URLs here, but which host is this? I don't know which host. So I need that piece as well. So that's why you can put more things to make this thing a little bit fancy. So for example, I will put HTTP host as another column, and then URE, and then I can sort unique, you know, all those things, all those fancy things, right? So let me actually get more first, and then I will do the fancy things. So this is actually a kind of a, you know, in Wireshark, when you click on something like, for example, ICMP and line, and then request tag. So when you click on that, you apply as column right here, right? You know that, right? You can apply anything as a column, and it will put another column at the end of your thing. See that request tag? So you can get rid of that by choosing unselect, okay? And it's exactly the equivalent in Tshark. If you say minus E, a column name, that makes it column. That's that easy. So here we have a bunch of HTTP hosts along with the URL. So what I'm going to do is I'm going to sort unique and look for the URLs, right? So, and I will do sort unique minus C. I would like to, and then sort again. Yeah, I just would like to give some example. Okay, now let's wait for that. Again, it's going to read the package from the bottom to up. I mean, up to bottom. And then it will give me the nice looking results, right? So this is actually what I'm looking. You can export to a TXT file and then use your favorite Excel to take a look at these things now. So you're doing the hard job and then Excel can do the easy part. So obviously these are Apple. I'm not interested in Apple. Google. So it's actually not a good idea. Of course, you have to filter that. Maybe grep minus V, Google, grep minus V, Apple. But I know what I'm looking for. That's why I would like to scroll all the way down. Here is the, supposed to be somewhere here. Yeah, instead of saying let's do that. And what I'm going to do is I will grep minus V. Grep minus V. You know what's doing grep minus V? Exclude, right? So I would like to exclude Google dot something, right? Because I don't want to exclude Google ads, maybe Google user kind of things. I want Google dot something. And also I would like to exclude Apple dot something. And remember, those are regular expressions. That's why there is a backslash at the beginning of dot. And this E stands for regular expressions, right? So see that, guys? So we actually taking advantage of command line tools along with the packet capture. So that's why, you know, Wireshark, although it's good to identify something, but if you are at a point that you are not getting a flexibility of command line tools, that's why you have to use Tshark. So at this stage, I see some American Online thing, right? Remember, we were looking for AEM, which is American Online Instant Messaging. So I see that there are some communication between Interoptic and Sneak33K, right? So these are the guys, and also if you look at these packages, send instant message to these guys, and the message is going to be, you have the cache. Actually, there is do here, do you have the cache? And the next one is, where is the next one? Supposed to be somewhere here. Okay, yeah, actually it's a little bit upper section here. Okay, yeah. So there is another one here that says be down in 5. Okay, so this %20 is space and 5 is actually 5 itself. And actually I can use some command line tools like Python tools to decode the text message as well. So I have a lot of flexibility, but obviously this thing is a communication between Interoptic and the guy which is called Sneak32K, right? Does that make sense? Is that clear? So, okay, this is kind of an introduction to Tshark space, and the next section we are going to analyze traffic, which is pcap 06 evidence 06.pcap. As you can see, it is 1.23 gigabytes. Yoo-hoo! So Wireshark is not going to be your friend. So we will try to open it with Wireshark. It's not going to work. But of course, we have a problem with this one, and we're going to answer this question. So in this case, and submit something to Google, and you have a case that is being said that N is an IP range of 192.168.99.0/24, but you don't know the exact IP address. And N is submitting something to Google, and it's supposed to be encrypted, right? So there is the game beginning again after the